workshop of the Chania. Also, I apologize because maybe some of the sun in the audience already heard about this law, but I think I prefer to keep it because it explains a bit what I'm interested in, and I think for this workshop, this opening action. Okay, so in all my talk, K will be a number field. Except at one specific point, but this will be just at the end. So K is a number field and X is a smooth geometrically connected variety over K. And so I will begin by giving some motivation and state the main conjecture about what I call the Tate Locus, but first defining the Tate Locus. So if we have y over x, a smooth projective or open system, I think an important problem in arithmetic geometry is to understand what I will call the typical locus of F, namely the set of points X, where if you look at some transfer power, the fiber at X, it carries an exceptional algebraic cycles. Say for some R. So this problem in general is very hard. We can try to simplify it by replacing algebraic cycle by motivated cycle in the sense of, for instance, Yves. And what this simplification allows is that for motivated cycles, you have a nice theory of pure motifs, so you can reformulate these problems in terms of algebraic groups. So this is the same thing as the locus, where the motivic Galois group in the sense of André as the. So maybe to simplify, I'm going to concentrate on the connected component. So this is during cycles and algebraic closure of the base field. So this is a set of points where the dimension of the motivic Galois group. So here my eta is the generic point of X. But so this is a group theoretic formulation. Perhaps a bit more tractable, but this is still very difficult because while motivated cycles are very close to algebraic cycle in a way. So what we can do is to tackle this problem is to look at its cohomological incarnations. And depending on the cohomology theory we are going to consider, the kind of feature of this problem we are going to capture may differ. So we can look at the singular incarnation, and this will give rise to the study of the Hodge locus. So I think there will be a talk about this by Greg Baldi tomorrow. And if you look at the p-adic etale incarnation of this problem, you get what I'm going to call the Tate locus. P-adic etale incarnation of this problem. This considers the system of this form, this system. And so I'm going to use notation about local system, which will be the main topic of this talk, during all the talks, so I'm fixing them here. So this is for an arbitrary QP local system. So I recall that this admits a nice description in terms of representations. This is exactly the same thing as the representation of the etale fundamental group of the base X onto any of the fiber. Should nice. The fiber this is a finite dimensional QP vector space, and this is very this is a functorial object. So for any point X and X, you can look at the morphism from the pi1 of the point, which is just the absolute Galois group. So residue field. I call this representation rho, I will call this one 2 back by X. And this is perhaps not crucial, but I would like to mention that if you take the generic points, it's the objective. And so I will move the talk. I will write pi p for the image. Pi p will be the image of the representation of the pi1, and pi px will be the image of the local representation of the point. And so this was subgroup of GLR, GLP. So these are p-adic groups. And I will consider also their Zariski closure. So these are those algebraic groups. And there is a third character which is important, which is when we look at the restriction of our local system to the geometric fiber of X. So here we have the geometric, the image of the geometric fundamental group. And it's Zariski closure. So I will use this notation around the top. Okay, so this is just notations. And so the Tate Locus of my local system is just a set of points where, similarly to the motivic splitting, the dimension of the local Galois group drops. And the main problem, so I would like to consider in this talk, is describe X locus, so the such. So yes, so those local systems, I will call them motivic to distinguish them from arbitrary local system. So the first remark is that if the local system, so of course this Tate locus, so I started with the motivic closed one, but you can define this Tate locus for arbitrarily p-adic systems. But so if my local system is motivic, it's always true that the Tate locus contains the motivic locus. So in particular, each time you can prove the sparsity result for the Tate locus, you will automatically get one for the motivic locus. This motivate this one, the one for motivated cycles, and if you believe in the analog of the Hodge conjecture for the p-adic etale cohomology, so it's sometimes called the Copernican Tate conjecture. Of course, conjecture leaves the two locus points. But of course, this conjecture is basically completely open. Okay. So this is the main problem. And so, as I said, if you look at the singular, the VHS, the singular cohomology, you will get the Hodge locus, and this Hodge locus captures somewhat more information about the geometry of the family. While when we consider p-adic etale cohomology, this has more an arithmetic flavor. And so what is really interesting for the Tate locus, which is probably easier to capture using the Tate locus than the Hodge locus, is the arithmetic of the Tate locus. So what is perhaps more, is really relevant as a question is to look at what I call the arithmetic truncation. So for every integer d, So we write just with this notation. So this is our close point, and smaller than d is just the set of close points where the residue degree is smaller than d. And perhaps the true problem here is really to describe so the set of points of bounded degree in the Tate Locus. Okay. And so I will immediately state what is perhaps the main conjecture and probably over-optimistic conjecture, but so I call it UOE for uniform open image. So if this is a statement, so if we take an arbitrary, not necessarily motivic QP local system, and if you assume a mild geometric condition, we call CGLP, so this is just an acronym for curve geometrically perfect. And the condition is just that for any morphism alpha from a smooth connected curve X K bar, so the algebra of the image with the phi1 of C acting on the fiber of your p-adic local system is perfect, namely as trivial abelianization. So morally, it means that if you look at the image of such morphism, for any open subgroup, the abelianization is finite. So it has basically, it's very far from being abelian. So if you have this geometric condition, the expectation is that so there are two parts. The first part is that we expect that the arithmetic truncation are not the Ariskidens. So this is the sparsity part of the conjecture, and the uniformity part is that if you look at the points of bounded degree which are not in the Tate locus, then the index, the image of such point in the generic image is uniformly bounded. So if you look at all point of bounded degree are not exceptional, and I bound on index. Okay. So I will explain the heuristic of this underlying this conjecture in a moment. I would just like to mention some motivations.
Can you say what you want? Can you say what is little x in condition 2? Where does that move?
This one. So you look at all the points of bounded degree which are not in the Tate locus. So which are
all the points of bounded degree which are not the Tate locus.
So this subgroup is an open subgroup.
Yes. And you look at the index.
Right. So you have a priori you have infinitely many such points. But the index is always bound, is uniformly bounded.
As a conjecture.
Yes, that's the second part of the conjecture.
Thank you.
The uniformity part somewhat.
Thank you very much.
Conjecture.
Geometrically perfect condition is automatic for motivic things.
Sorry?
I guess the CGLP condition.
Yes, yes, I should have said that for motivic local systems, this algebra is semi-simple. Yes, briefly the kind of motivation for this conjecture. So first, of course, because of the this inclusion of the motivic locus in the Tate locus, this automatically implies the scarcity of itself, so namely that it's not the incidence. It's the typical special case of this observation, but there are several others. That if you look at a set of points of bounded degree, where the rank of the Nero-Severi group, the family jumps, this is not the incidence. You can play with motivated cycles and other application. So this is really a consequence only of the first part of the conjecture, and if you have the two parts, this gives some uniform boundedness results for invariant which are somewhat encoded in p-adic etale cohomology. So here a typical kind of consequences is you look at the order of the P-primary part, the P-silo of certain abelian group. These again are going to be uniformly bounded for points of bounded degree. So here's the kind of group you can take for AX. It can be you can look at the Albanese, or you can assume Y if you prefer is an abelian scheme. So you can look at the co-rational points, and you look at the P-silo of the torsion. And so this tells you, in particular, if you apply this one, so for instance, if you are able to prove this conjecture for the Tate module of the uniform abelian variety over AG, we will get the P-primary part of the uniform boundedness conjecture for abelian variety. So I think there was a talk about this subject last year. And you can also take, for instance, the Galois invariant part of the geometric Robert group, and again takes and twice. So infinity.
Sorry, Emma?
Yes.
In that conjecture, X, does that mean projective or no?
No, not this.
So why can't you, I'm just confused. What if you take like P1 minus 3 points and take some local system there? What won't be satisfied? Which of the assumptions won't be satisfied?
I don't so what no, I'm not sure. If it is GLP,
Sorry? Yeah, of CGLP.
yeah.
Just take P1 minus 3 points, take some local system.
Yeah.
You're saying that there's only one curve there because it's a curve, and you're saying it to be a billion, or I'm confused.
What is a billion?
I'm just trying to understand why one isn't contradicted for like P1 minus 3 points and some local system there.
I'd be interested if you found a counterexample, but
No, I'm saying something very stupid, so probably, okay, I'll probably confuse.
CM points are bigger and bigger.
Sorry?
The CM points are bigger and bigger fields.
CM points over bigger and bigger fields.
Here I take points of bounded degree. Of course, if you take all close points, yeah, of course. But what is crucial is the
The picture confused me. I understand.
yeah, sorry, this is
Thank you, sorry.
so yeah, I know I have to still make some progress with notation. Okay, so this is just to give some concrete application of this conjecture. But as you will see, there is for the heuristic we have currently, there is a main obstruction to this conjecture as soon as the dimension of X is larger than 2. And also things that again, if the dimension of X is larger than 2, the D larger than 1 is definitely too optimistic. So I think to really talk about the conjecture, it's better to take this one, namely only the set of k rational points in the Tate locus, not the esquidance. Yes, unfortunately, I'm afraid so this conjecture is too hard, but what you can try to do is, just as in the Hodge theoretic setting, you can stratify also the Tate locus by the structure of the local monodromy group. So maybe we can look at specific strata, which might be more accessible. And so there are two ones, I think, are arithmetic interest. So in this Tate locus, you can look at what I like to call the toric locus. Tor is not for torsion, but for toric. So this is just the set of points where the local monodromy is the torus. And of course, so that it be really contained in the Tate locus, I make also here the assumption that the geometric monodromy is non-trivial. And inside this, we have another even more degenerate strata, which is what we call the trivial locus, which is just a set of points where the monodromy is trivial. And this is actually, you will see, of arithmetic interest, while it's not really in the theoretic setting. And so these are what I call the toric locus and the trivial locus. And of course, the toric locus is the analog in the etale p-adic setting of the CM locus of VHS, variation of a structure. One remark is that, contrary to the case of the Hodge theoretic case, we do not know that the action of Galois is simple, and this is a source of trouble. So we could be perhaps more natural to consider some non-reductive variant of the locus, so the set of points where the group is solvable, and here the set of points where the local monodromy is unipotent. But this is more difficult to investigate. So for the moment, I would like to focus on the toric and trivial locus. And so the conjecture for those locus are rather simple to formulate. So assume you have a true local system, the geometric monodromy is non-trivial, then the conjecture for the toric locus just the same one as here, except that here for, I think it's more optimistic to expect the statement to be true for every integer, D. So it says that the set of points of bounded degree in the toric locus is not the esquidance. And this is a shortening notation. And for the trivial locus, the conjecture is that it is just trivial, it's empty. As you said. Okay. Yes, I would like to give perhaps a reformulation, some true reformulation of the conjecture about the trivial locus. One says that if you take any close point, then the image of the whole monodromy is normally generated by the image of the local monodromy of this point. And the second reformulation is that if you take a ZP lattice, which is so a ZP model of your QP local system, so a ZP lattice, which is a random fixed invariant. And if you look at the connected etale cover, which corresponds to the kernel of by one effect acting the reduction modulo Pn. So this is if you want the full level Pn structure of your p-adic local system, then you get a projective system of the cover of your variety X, and what the trivial, the conjecture about the trivial locus says is that you have no projective system of clear rational points in this projective system. And of course, you can replace K by any number finite field extension of K.
Excuse me, I'm sorry. The last conjecture here, I'm not sure I interpret. Are you saying that there are no algebraic points with
yes, and probably the interesting case is this.
Yeah, no algebraic points or close points with the property that the mononomial is finite.
Exactly.
Why would you suspect that?
Because it follows from the, I don't know, at least it follows from the unramified content-Maser conjecture.
Pardon me? It
follows from the unramified. I will try, maybe so this uses some variational p-adic sharing. So maybe this is the sequence of my talk, so maybe we can.
But for example, if I have a zero-dimensional variety,
then it will have this.
And I have a finite local system. I can.
Yeah, of course. I assume that the geometric monodromy is not is infinite. It's a true really varying. Yeah, of course. Otherwise, another way to say is that if this is non-empty, then the geometric monodromy is finite. Then the local system is trivial. Yeah. So as to answer Ellen's question, I would like to explain what are the, at least, so those three conjectures are themselves consequence of more classical conjectures. So this is also actually a part of the motivations. These are some test conjectures. So the uniform open image conjecture, so at least for this one. So this one should follow from, and this is why I think it's too optimistic, from the Bambiri-Land conjecture. So the one saying that if X is of general type, this implies that the set of irrational point is not an evidence. So this is actually this implication is itself conjectural under a conjecture which I call the level conjecture, and I will try to give you a formulation of it in a moment. But once we have this level conjecture, this implication is rather simple. It's just uses formalism of Galois category and some basic structure of p-adic group. The toric conjecture, at least if you assume that your p-adic local system is motivic. So this one from the generalized Andreev conjecture. So here I think there are people in the room which know this much better than I. But it says that so this is modulo the Mumford-Tate conjecture, because if so you are in a motivated setting, you can this toric locus is going to correspond to the CM locus of the corresponding variation of Hodge structure of the singular local system. If you look at the Betti homology, and for the in the Hodge theoretic setting, we have this so this generalized Andreev conjecture, which says that if you look at VHS and the identification of your variety with the Zariski dance set CM points, then it should factors through dominant morphism to Shimura variety. And the local the VHS come from the one on the Shimura variety. And on the Shimura variety, we know that the set of points of bounded degree of CM points of bounded degree is not the residence. So this uses the complex period map in the spirit of the Pilazzani strategy for André Hort. So it doesn't, I think this implication doesn't really use o-minimality or difficult transcendence result, but it uses the average converse conjecture. It's a rather non-trivial implication. And so for the trivial, the conjecture about the trivial locus, as I said, it really follows from the unidentified Fontaine-Mason conjecture. This conjecture says that if you have an open subset, which is the ring of integer of your number field, which contains all the place that divide P, then if you take any QP local system on it, it's finite. So this implication actually, so if you want to assume.
So, what? First, you need that it's geometrically reducible.
I think the unramified Fontaine conjecture is the unramified one, not the Fontaine-Mason. But I think it follows from the Fontaine-Mason conjecture. So I'm just looking at the p-adic Garras representation, which is unramified at all place V dividing P, and then
I mean, if I take a smooth projective morphism over an open of
no, but here I'm on open of the ring of integers. This is not on the geometry.
I take a smooth projective morphism over an open of a ring of integer, open of the integer of a number field, and then why should it be the case that this the local system, the Gauss-Manin of this is trivial after finite cover of the after allowing an extension of the number ring? And maybe I'm saying nonsense here. The unramified Fontaine-Mason. I mean, Fontaine-Mason is if it's geometrically irreducible and arithmetic, then it should come from geometry.
Yes.
But coming from geometry, of course, finites are coming from geometry, but they're not the only ones.
Of course. Yeah.
So why is that?
The fact that it follows from the Fontaine-Mason conjecture, I think, is not trivial. It's a paper of Kissin, but I couldn't tell you how it.
But Kissin has more assumption. Well, it doesn't matter. I will
but anyway, this conjecture is formulated in the paper of Fontaine and Mason.
So you mean Kissin-Wortmann, right?
Yes.
Yeah. Oh, okay.
I think in their paper there were some assumptions which were proved afterwards by other people, but I don't. Anyway, this is the original conjecture.
I know what you refer to now. Yeah. Okay. Yeah. Let me think. Yeah. I apologize for the question.
No, it's yeah. So actually. So if you want to prove, if you have another way to formulate this conjecture just by contradiction is that if you have a trivial point, then you want to show that the local system is essentially finite, and as we are over a number field, actually by inverse reducibility, it's enough to show that for all close point, it just to show that actually all the points, all the plus points are trivial. That's reducibility. And so, and the way to prove this is to use some part of the variational, the periodic Hodge theory, plus the theorem of Sen. So plus, as I said, the ingredient inverts irreducibility. So the way to use this rational periodic Hodge theory is to say that if I have a trivial point, then if I take any place V dividing P and I look at things over KV, these trivial points, finite representation is in particular Hodge state with a single Hodge state weight 0. And this by the recent result of New and other. So these properties transfer to all the points. So for every point, you are at all place V dividing P, you have a Hodge state with a single Hodge state weight 0. But Sen's theorem tells you that actually this is equivalent to being potentially unramified. And then if you are potentially unramified, you can of course replace X by a finite cover and make everything torsion free. So this means that you are unramified and then you have to do a bit of class field theory and to show that this is actually finite. So this is the way you show that this follows from the unramified Fontaine-Mazer conjecture. Okay, so this is a bit the kind of problem I'm interested in. And so in the second half of the talk, I would like to give some, explain what we can prove for the time being, which is depending on the time I have, we'll give some hints about the proofs. So I will start with the uniform open image conjecture, and I will also try and explain. So I'm just erasing it, but what is this level conjecture? So for the UV conjecture, so we have it's Akio Tamagawa, so already some time ago. I will prove it when the dimension of X is 1. So this is for all D, and this is the only reason I have currently to formulate it for every integer D, but of course this kind of problem is there is really a dichotomy between the pure case and the higher dimensional case. And so I'd like to give the strategy of the proof, which is relatively, which is naive, perhaps probably too naive. So the first is to reformulate it in Diophantine. The first step, so is to reformulate it in Diophantine terms. So this only uses the formalism of Galois category and a bit of some play with what is a p-adic group. So the output of this is that there exists a projective system of finite etale non-connected covers of X, such that the exceptional, the Tate Locus is exactly the set of rational points, and the Tate Locus is exactly the set, sorry, the image or rather, yeah. So the set of rational points is the Tate Locus is exactly the set of rational points which lift along this cover. This. And furthermore, for the uniform part, you can show that so if you look at the points which are not only not in the exceptional locus, but maybe you have to enlarge a bit. So actually those who do not come from a certain level n, so these have a uniformly bounded index. What is not, so this property comes from the construction of this tower of cover, which I'm not going to review, and which is not very difficult. So this is what we have to prove the conjecture. It means that there is no projective system of k-rational point on such this tower. And we have very few ways to prove such a result in general, and I think the only general conjecture predicting this kind of result are those of the form some geometric property implies some arithmetic condition, and the main conjecture is that it's Bombieri long. So assuming Bombieri long, what we should be able to prove that Xn dominates a variety of general type for n large enough. So if we are able to prove this, this would imply by Bombieri long that for some L, the set of rational points is not the residence, and a fortiori this will be not the residence, and the image of this for the second case for the uniformity part will be not the residence. So this is really the purpose to prove that for n large enough, the set of k-rational points is not the residence. But this conjecture, so as you know, is known in very few cases. Not if the dimension of X is 1, because this is a model conjecture. And it's also known if X is a subvariety of an abelian variety. The consequence of this, so this is also a theorem of all things. And the consequence of this, which was observed by Frey, is that so if the dimension of X is 1, and then for every integer which is smaller than the integral part of the geometric gonality of the curve, so I think the exact form is this, the set of points of bounded degree on the curve is finite. And it's open, I really think, really almost entirely open. If the dimension of X is larger than 2 and you are not embedded into an abelian band. So this explains already, I think, the reason why our theorem is only under the assumption that the dimension of X is 1. And in view of this, the main work, what was difficult to prove is that, so we have to prove G, so the geometric part using the GLP assumption. So the main contribution was to prove that the genus of these curves are going to infinity with n, and so this argument was using some, what I would say, of an abelian flavors, in the sense that the issue is that if you want to show that if the genus goes to infinity, you can use Riemann-Hurwitz formula. And but to use Riemann-Hurwitz formula, you have to understand the ramification of your cover. And so the issue was to extract this information from the representation. And for this, we have to do some p-adic analytic geometry in on the orbit of the representation. And one key ingredient, for instance, is those bonds of Serre-Sterle for the reduction, the number of points on the reduction modulo Pn of the p-adic analytic variety. And once you know that the genus goes to infinity, you have to we prove that this implies automatically that the gonality of the curves are going to infinity, and this is using some technical results about the geometry of curves, so I'm not going to give any detail. And of course, so now you can also guess what is just the statement of the level conjecture. So for x of higher dimension, so the main conjecture is that this is true. So I do not know how to prove this by our methods for the time being. I would like to mention that if you have a motivic local system, you can, as this being a general type is a geometric condition, so this is really a condition on the local system on x over k bar, not over k. So if you are in a motivic setting, you can really reformulate it into a condition on the singular local system underlying the ZVHS. And so the analogous question is the following: if I have V infinity say polarizable ZVHS Xn, and if you take a sequence of a subgroup, of the image, a strict decreasing sequence of the image of the topological fundamental group, the question, so this corresponds in terms to a sequence of cover of your variety, and the question if algebraic cover, and the question is whether this becomes of has this property. So you may, I think, also assume that the complex period map is finite to one by Griffith's conjecture, which was proved by Gwenaelle, Jakob, and Johan. So you can make this assumption. So under this assumption, can you prove that Xn is of general type for n origin of this somewhat odd theoretic formulation?
Sorry, right is not so good. So maybe could you repeat the assumption, just the assumption?
So I take a polarizable ZVHS on the identification of my variety.
Can you say without acronym? It's difficult to
polarizable Z variation of Hodge structure.
And on the upper part here, you have an extra assumption.
Yes, the corresponding complex period map is finite to one. It's finite fiber, or maybe I don't know this. And so I take I look at the image of the topological of the monodromy. So this is now a subgroup of a discrete subgroup of GL n of Z, and I take a decreasing sequence of subgroup strictly decreasing. So this corresponds also to etale cover of my variety. And the question is whether this becomes of general type for n large enough. So that's the odd theoretic incarnation of this question from. And I would like to mention that Johan Gwenaelle, for instance, as a result of this type, if you take for gamma n the full level n results, and actually the proof, the curve case with Akio, the first step was to prove this for exactly the full level structure part of the problem. So somewhat the result of Johan Gwenaelle shows this part, and now I don't know if experts, I think here we have much more powerful techniques to prove those kind of results than on the book. So I want to ask this question to some people in this room are expert of this. Okay. Okay, so this is all what I wanted to do for the uniform open image conjecture. So the Tate Locus situation is at least we have some partial result without restriction on the dimension of x. Actually, there is no assumption on x. So this is the result, this is the Stix. So it is basically finished, but not the writing, unfortunately. So the assumption is that, so this is for motivic local system, and actually slightly margin different, so that I will call part of a motivic datum. So which means that I assume that I have all the data which you are familiar with when you take something motivic. So you have a Q-compatible family p-adic etale local system with p varying. You have a singular local system and a vector bundle with connection and a Hodge filtration. You have a VHS. And you have all the compatibility property you require, in particular, also the one, the property of being the rampant in the sense of the adic show. So I don't want to give details, but you really require all the possible conditions you image. And under this assumption, so of course, a typical example of a adic local system which has this property as the one. So under this assumption, and so I have a respective part of the statement, which is that, so if we assume furthermore that the complex period map corresponding to the VHS is finite to 1, and we also need some level condition. So I don't know if it's really important if I mention it. So this is roughly says that the image of the monodromy is properly for at least 2 different primes. So morally, it means this will imply that everything is torsion-free, all the algebraic groups that appears are connected, and so on. Then, under those assumptions, there exists a set of prime of positive Dirichlet density. Such that you have what you expect, unfortunately not for points of bounded degree, but only for k-rational points. Well, if you look at the component of your compatible family, which are indexed by the prime in P, and in the case the period map is finite to 1, you can prove. You can do better, you can show that this is finite. So I would like to comment immediately that I don't know, I'm not sure I will give details about the proof, but our proof, we are very pessimistic about removing this set of prime of also positive density, where we cannot control things. This comes from the method, but we are more optimistic about proving the result for arbitrary D, still for a set of prime of positive density, because of this respective part. And maybe we can try and implement a kind of symmetric power argument to try and capture points of bounded degree D.
That's for curves or for?
No, that's for arbitrary, that's the point, yeah, otherwise,
Yeah.
For curve, we have already a much stronger result, so for curve, everything is done. So maybe, so maybe it's better if I explain a bit about this result, and I'm just going to say in a nutshell what we can put for the Tate Locus. So maybe this is more relevant actually to what we are going to investigate this semester, this year. So maybe, yes, I can say a bit about the strategy. So in one word, this is the Lorentz and Katech strategy for proving strategies they developed to give a new proof of model conjecture and also tackle and give some sparsity result for integral points on higher dimensional variety in presence of somewhat local system with certain property on the monodromy. So the step is in the strategy, sorry, is in three steps. The first, we fix a nice compactification, normal crossing compactification, and we extend it on an open the ring of integer of our base field. Like this. This is a smooth normal crossing compactification. And the first step is and extend all our motivic data to the boundary component where the monodromy is finite. So here we add the component D where the geometric monodromy is finite, and actually it's trivial because of the level assumption I made. So this extension step is uses really heavy machinery, because the issue is that we have to extend, keeping all the nice compatibility property between the objects. So we need to extend the VHS, we need the independent orbit theorem. To extend the family of the Q-compatible family, we need in particular the companion conjecture, because we want to preserve Q-compatibility. We want to preserve the fact that we have somewhat integral polynomial of Frobenius, because in this Lorentz-Cadoret strategy, there is at some point so-called fighting lemmas that we need to use. We need to keep purity and so on. So this is not trivial, and we also need some variational p-adic Hodge theory, because we want to keep this property of being a de Rham pair. So this is really actually not an easy step, but the machinery was developed by other people than us. And once you have done this, so you replace X by this somewhat partial compactification, and under this assumption that the monodromy is really infinite on the boundary, you can prove that the CM points are integral. So in that case, you can prove. Sorry, I said CM points, but I'm sorry. Maybe I should put this open more. This part of the argument is I'm not going to give details here, but this is exactly the same flower that I think there is this in the paper of Jakob and Ben. And so this is crucial, because the Lorentz-Cadoret method is really not for k-rational points, but for integral points. And once we have this, we can run the Lorentz-Cadoret method. So for this, so the local system we use is of course the one we have. And so for this, we need to fix a certain p-adic, a certain place good reduction. We divide P, and this is the choice of this place, which is going to impose some, we have some constraint, and this is why we can only catch a set of prime of positive density. This is because the method is not going to work for arbitrary V. And maybe what I should say is that those will work for those where we have some ordinary condition, ordinarity condition. So if you really make explicit the method, what you need somewhat is that the rank of your Frobenius, so you have a X toric point, directional point, and you have your place V, and so you have somewhat a Frobenius at V. And so what you really need is that the rank of the torus attached to it, or if you want, you take the group it generates and its directly closure. So this is a torus because this is contained in the torus. So it has to be the same as the rank of the global, actually the local image, but what we can only control somewhat is the global image. And so under the assumption of the defining condition of what it is to be a motivic data, we know that there are only up to isomorphism, only finitely many Galois representation corresponding to toric point. We may have infinitely many toric points, but only infinitely many Galois representation. And this, and for this, we know this condition is independent of P. And what we need to ensure is that for all toric points, we have this condition on the rank of the Frobenius. And for this, we can Serre is going to tell you that this condition is going to be true for density 1 set of place of K, and you have finitely many K, so you intersect your density 1, you still get something density 1. But when you look at this in Z, this is going to give you a set of points, a set of prime of positive density. So this is the set of, in the end, the set of prime which appear in the state. Okay, so I think I'm about out of time, so I'm not going to say almost anything about the trivial conjecture for the result. Sorry, about the trivial locus. So what we can prove in a nutshell for the conjecture about the trivial locus. So you can formulate also a p-adic version of this. This is, you can ask what happens for K over QP a p-adic field. So here there is no hope that the conjecture, as I stated, is be true. What the best you can expect that the trivial locus is everything if it is non-empty. This will not imply that the local system is finite, because in the p-adic setting you may have some combinatorial part of the pi one that we cannot capture. And what we can prove is that we can prove this conjecture assuming a Q rationality condition on the local system. So in particular, it implies the conjecture when your p-adic local system, and it implies the conjecture of the number field when your p-adic local system is part of a Q-compatible family. And in general, the techniques give some kind of wake form of the conjecture. I'm not going to state. And again, the ingredients involved in the proof of this result are also some variational p-adic Hodge theory. We also need the companion again, both the L-adic and the p-adic companion. And we need also, and this is perhaps the main technical contribution, to say that this is with Tamagawa. So the perhaps our main technical contribution is so to apply the companion, you need to have something over a variety over a finite field, and to get something over a variety over a finite field from something variety on the p-adic field. You need to choose a model. So for this, we can use potentially semi-stable reduction theorem after reducing to the case of curve. And then you need to extend to your model. And for this, we use, so the input that you have a trivial point, as I explained already when I discussed the relation with unramified Fontaine Maser conjecture. So if you have a trivial point, this will automatically imply that all your points you are going to be potentially unramified. So after finite extension, you are going to be unramified at all points. And what we show is that this implies that the local system extends to the compactification of the model. And then we can pass to the special fiber and apply companion ones. Okay, stop here. So.
Questions for the speaker?
Can you state this theorem? I'm just not sure I completely got it. So
Wait, what?
can you just state the theorem about the trivial conjecture again? I wasn't sure I caught it.
So the theorem is just like that. Maybe I can. Yeah. You have to have a 3P adic field. So now X is modularity over adic field, and so I assume UP is a QP local system, which is two rational, meaning that each time that you have a characteristic polynomial of Frobenius coefficient Q of T, and then just prove that if the trivial locus is non-empty, then it's everything. But yeah, I'm saying this not necessarily implies that geometric monodromy is fine because we don't have Shibota-Ref or Berthier reducibility.
You get something, I mean, this is a stronger theorem than if you just asked about the locus where you have class, the Tate locus or the Hodge, I forget what you called it, sorry. But if you have a geometric family, you have actual classes, then this is a stronger theorem than if you just asked for that not being Zariski dense.
Which
So you're looking at XVP, right? Where you have extra Tate classes in your
Yeah.
local system. So if you just ask for actual algebraic cycles, like the motivic classes, that would be an even smaller set.
yes, a priori.
Can you prove more about a priori, right? Can you prove more about that? Can you like the statement with like do you get any mileage out of that, or is the method just you pick one of these P's and you use that representation?
Don't think we can.
Okay.
Unfortunately,
No. Okay.
so much it's because we cannot understand. I mean, I cannot understand algebraic class that I pass to Galois invariant class, which I understand.
Sure.
Better, but no, yeah, unfortunately.
Oh, that's great.
If there's no more questions, let's thank the speaker again for being